Okay. Hi everyone, I'm Finn, and I'm a postdoc working with Stuart Sim at Queen's University of Belfast. And today I'm going to be talking about the impacts of helium in the spectra of double detonation models. So just for the uninitiated, people aren't familiar with the kind of work we do, just a little bit of background on kind of the simulation pipeline we use to simulate Type Ia Supernovae. So focus of our group is radiative transfer simulations. But if we need to start out with some kind of initial guess what we think regenerative model is, and we work closely in collaboration with experts in hydrodynamic explosion simulations. So in Fritz Rupke's group in Heidelberg and also Rudiger Packmore. So when we start out with the initial guess, they carry out these multi-dimensional hydrodynamic explosion simulations followed by a nuclear synthesis post-processing step. And then this acts as the input to our radiative transfer simulations. So we take these densities, velocities, and compositions, and then we use our three-dimensional time-dependent Monte Carlo radiative transfer code ARTIS, and we basically simulate how photon packets, which are these little black blobs here, move throughout the ejecta, interact through various processes, and then we can bin them by wavelength, and that gives us spectra and light curves, which we can then kind of directly compare to observations, and then you can go back to the progenitor model, see kind of how good a job it does for explaining that. In this talk, I'm going to be talking about the role of helium in double detonation models. So this is just a 2D slice through an explosion simulation of a double detonation model. And the point here is just that quite a robust prediction of these explosion simulations is quite a significant amount of unburned helium in the outer ejecta. So the question then is, if there's this unburned helium, is there then going to be a spectral signature of this helium that could potentially link the double detonation scenario to observe Type Ia supernovae? But simulating spectral contribution of helium in radiative transfer simulations is a little bit more complicated due to the atomic structure of helium. So as you can see, the first excited states of helium here are close to 20 electron volts, and they're also metastable states. And actually, the temperature of the ejecta in Type Ia supernovae is actually not sufficient to thermally excite electrons to these excited states, which means that the population of these states is actually dominated by primarily excitation, and actually what dominates is ionization from fast non-thermal electrons. So if you want to accurately characterize what these features might look like in a simulation, you need a full NLT treatment of the plasma conditions, including treatment for these non-thermal electrons and forbidden transitions. So the simulations I'm going to talk about for the rest of this talk are all carried out using this full NLT and non-thermal treatment that was implemented in ARTIS by Luke Shingles. So just a little bit of background from this was a previous simulation that was carried out by Fionntan Callan. So this is a one-dimensional full NLT ARTIS radiative transfer simulation for a double detonation model. And this model had around a solar mass, total mass, about half solar mass of nickel, and helium mass of 0.018 solar masses. And from the simulation, you can see that around 5 days after explosion, so this is in the near infrared. I should have mentioned the kind of feature I'm going to focus on here is this helium 10830 line. And you can see that around 5 days after explosion, the helium 10830 feature is blended with this magnesium 2 feature that's quite widely suggested to be seen in normal Type Ia supernovae. But actually, by around 8 days after explosion, you see that in the model, actually the helium separates to form a distinct feature. So you get this kind of double dip. And actually, when you compare it to this transitional IPTF13EBH, you see it also produces this kind of double dip feature. So this is potentially evidence that we've actually seen a signature of the double detonation scenario in an observed Type Ia supernova. So then this motivates that the work that I'm going to be talking about for the rest of this talk, which is basically this is one realization of it. We want to investigate what it could look like for a different model, which has quite a different structure for another double detonation model. So the model I simulated was based on a three-dimensional double detonation explosion model from Sabrina Gurnall, and basically produced the 1D model by spherically averaging over kind of representative direction in the 3D model, which is kind of roughly marked out here in that slice. And while the total mass and the nickel mass are quite similar to the model that Christine simulated, the helium mass is around double of that. And not just that, so these are just the kind of ejector compositions. So Christine's model on the left and my simulation on the right. And if you particularly focus on the dark blue line, which is helium, you can see that while the umbrant helium kind of doesn't start until around 15,000 kilometers a second in Christine's model, in my simulation it actually goes down to around 11,000 kilometers a second. So we want to see what these differences between the two models, how that kind of shows up in the synthetic spectra that we get. So I'm going to be comparing to 2011 FE that represents sort of the normal 1As, and then this 2022 XKQ, which is another one of these transitional type 1As. And you can see this is just the optical spectra around peak with the model in blue there. And it produces kind of overall reasonably good agreement with both of these objects. So it's kind of reasonable to be making these detailed comparisons in the near infrared, which we're going to go on to talk about now. So I'll just keep that kind of double dip feature from Christine's simulation on the left there. And now we're looking at near infrared spectra for 2011 FE, and then just to zoom over the kind of 10-830 region on the right there. And we've got the standard model in blue, and then in the red, we've got the model in which we don't include line opacity from helium. So basically, by comparing the red to the blue line, you can see the contribution from to absorption from line opacity from helium, which we can sort of isolate the contribution of helium in the spectra. And if you kind of focus on this far right plot, you can see again we predict this helium feature forms, but it's quite different. So it's much stronger and more persistent than the feature seen in the previous model, and it's also never forms this kind of secondary component. So what it does show is that it's basically pretty strongly blended with this magnesium-2 for all epochs. And it's been suggested for 2011 FE that there's actually an extended wing to the blue wing of this magnesium-2 feature. And it was previously attributed to carbon-1, but we don't see any carbon-1 in our models. So from this simulation, it seems more likely that this, while the helium is too strong for this particular realization, it's possible that helium could be contributing to the blue wing of this feature in normal 1As potentially instead. And then just kind of right on the point that we're obviously not seeing this double dip. If you look, this is the same plots, but compared to 2022 XKQ, you can see that we're obviously not producing any of that sort of double dip feature. So I think the overall point is that for two different realizations, the double detonation scenario, we get a kind of completely different evolution of the contribution of helium to the spectra. Which can depend on the type of explosion model, type of double detonation model, or also the line of sight that we look at the model from. And just a little bit of a comment on the contribution of optical helium. So normal 1As don't really show clear optical helium spectral features. So it would then be a problem for the double detonation models if they predict very strong optical helium features. So the strongest is the same type of plot again. So red to blue to show the impact of helium. The kind of strongest helium feature is to the blue wing of the silicon, I think 5972 or whatever it is feature. And you can see that it just kind of blends with the blue wing, and it's kind of hard to tell whether it would be the standard model or the model with no helium, which produces better agreement with 2011 FE there. So basically just to say that we don't see any clear optical helium, so that's not going to rule out the double detonation models here. And one final point before I get to my conclusions. We see some weak carbon-2 in the simulation, which you can sort of roughly see from this plot. But we never see any carbon-1 that's been suggested that might explain these kind of this secondary feature or the extended wing in 2011 FE. So just because you have carbon-2 doesn't necessarily mean you're going to see carbon-1. And yeah, I'll leave you with conclusions. The paper's now on archive and it's interviews, so if you want to have a look or send me any questions, let me know. I'm happy to take any questions.